Guys, does anybody need this handout to go through the micro? So. Does anyone need this handout? Do you need it? You need it? What's happening? Okay. Alright. So you guys are like, I'm not sure if I need that. Can you get one of those men there?
Appreciate it. I don't think I get up.
You better think of it. Alright. Yeah. You need one? Okay. Anybody else need this handout here? Anybody else? Okay. Don't leave it open. You letting somebody in? Good. Okay. So let me ask one more time, does anybody still need this handout? You need this handout from yesterday? Okay. What's up? Who needs? Anybody else need this handout? Sure when this is sticking. Okay, here we go. Okay, you need one? Okay.
I'm sorry.
Okay.
That's my folder.
It's okay. All right. Does anyone else need this handout? Okay. All right. That should be it. Okay. So, we've so far. So, guys, tomorrow, at this moment, with your mindset, this is gonna be great. But just to remind you, what do we have tomorrow? So the quiz is gonna be. I'm gonna focus on 4.9. I'm not gonna put a Newton's method problem on there. I'm gonna let you guys have some more time to work on Newton's method homework. I'm gonna focus 4.9, which is just antiderivatives. So the better you are with derivatives, the easier that should be. Yes?
So quiz tomorrow is only 4.9.
Quiz tomorrow is only 4.9. If I put any 4.8 on it, Ryan, you're allowed to kick me. Now part of his brain is like, oh man, it'd be great if Jeff forgot. Just let me kick him one time.
You got the anti-derivatives worksheet?
What are you talking about?
4.9 worksheet maybe from yesterday?
I gotta find it, I'm sorry. Somebody else asked me for it, I have no idea. Is it the
Don't worry about
Don't let me
it.
forget. Forget about it. I like that. I want everybody that interacts with me to do a little dance. Alright guys, so 4.9 was all about antiderivatives. What was one big thing about antiderivatives that a lot of students forget? Plus C. Okay. So don't forget, when you're doing an antiderivative, specifically, I'm going to use a word that we haven't used yet. When you're doing an indefinite antiderivative, so you're not given any information, then we got to have a plus C. If I give you information, can't you solve for C? Okay. Okay. So 4.9 is just about antiderivatives, which makes sense because everything up until that point was derivatives. So now we're starting to get into the opposite. What's really weird and what I try to get you guys ready for is we do antiderivatives, and then it seems like we do something completely separate, which is areas. What we're going to do today is we're going to connect finding areas to finding antiderivatives. For a lot of functions, the antiderivative is pretty simple, right? Do you all agree? Well, let's do this, and then you will very much agree that doing the area this way is horrendous. So we're going to do it. You're going to have to do it. And then we're going to learn the shortcut. It's sort of related to the limit definition of derivative. All right. So I have one example here. This is very useful stuff right here. So this is a really good sheet to have sitting next to you as you're doing section 5.2 homework. That's what this is from. 5.2. So, on the back of this. This would be a nice little review. We're going to estimate what the area is. And then we're going to seemingly do something unconnected. We're going to take this guy's antiderivative, but we're going to use the process. And just to remind me, this formula right there, what is the n? physically represent? How many rectangles? Cool. And so, the more rectangles there are, the better my resolution, the better my approximation. You with me? Because if I use a square-shaped side, I know it's a rectangle, but if the top is flat, it's not going to fit perfectly over a curve. But the smaller those rectangles become, the more they can all fill it in better. So of course, if I let the number of rectangles go to infinity, I'm going to have a perfect answer. Is everybody with me? And we know about limits. We've done a lot of limits. And some of you guys were hoping they were gone, but they just never leave. They're going to keep coming back because they're so freaking useful. Okay, so this first one is a review. This first one is that concrete stuff we did. Where am I going from to on this problem?
0 to 3.
0 to 3. I'm just giving the graph as a place to put your rectangles. Are you with me? So let's see. And I say to use left endpoints. So let's come back to that in a minute. What's the very, very first thing I should do on this problem? Yeah, I want to make four rectangles. So how can I use that to figure out something important? What's the width? I love it. So how do I get the width of my rectangles? And let's see if this makes sense. If I know how far I gotta go, and I know how many steps I gotta take, like each rectangle is like a step. If I divide those, I get how big of a step, how wide the rectangle has to be. That physically makes sense. Okay. And the higher up you get in math, the more you're like, thank God that actually makes physical sense. So the width will be the distance I've got to go, b minus a, divided by n. So each wrangle? Yeah, sure. Each wrangle is going to be 3/4 wide. Each rectangle is going to be 3/4 wide. So I start at 0, right? Where's the first rectangle end? 3/4. Where's the next rectangle end?
1.5.
Yeah, 6/4, which is 3/2, is just 1.5. I like everybody with me? So you can just put 6/4, who cares? Where's the next rectangle end? Oh, sure. Wouldn't really be there, but it's okay. 9/4, which is like 2 1/4, right? But it's sort of in the wrong place, but I'll be right. And then the next rectangle, 12/4, which is 3. Sweet. So see how that verifies that we've done things correctly? I'm supposed to stop at 3. So if you miscalculate your width, you'll very quickly see you did. You'll see that there was a mistake because you don't end where you're supposed to end. How are we doing so far? What does left endpoints tell me?
Means you start from 3, go to your first point, right?
No.
Oh.
It's an underestimate.
How tall would that first rectangle be? It's going to be dependent on its left side, right? So when I make this first rectangle, it's going to go from here to here. So it's going to be this tall. Is that cool? The left side, right? If it would have been right endpoints, the first rectangle would have been this tall because it would have been based on the right side of it and how far that side goes. Yes? Is that cool? So let that piece be nice. And then I keep going. The next rectangle is going to be as tall as this here. And then the next one is as tall as this here. And then the last one's as tall as this here. So they're each as tall as the output of their left side. If I did right endpoints, that would have been different, yeah. Do you see how this is kind of nice? Do you guys, can you tell from the picture this is an over or an under?
Under.
It looks from the picture like they average out. It looks really difficult to tell which one it is. Because that overage seems to fill in that underage, right? So forth, just to make up some words. Why would I expect something like that to happen? Because this function is symmetric, right? And I'm sort of going around the middle of it, so I would expect that. Does that make sense? Okay. So, how do I do this? Let me see if you guys are cool with this. I'm going to write down in general what we're going to do. Each rectangle is going to look like width times height, correct? So if let me see if you guys, so it's gonna be width times height, plus blah, blah, blah. So I'm gonna take the width out, and then I'm gonna have a bunch of function values. You see, remember yesterday, I can factor the width out? You guys remember this? Each one of them has a width in it, so I can factor it out. It stays the same. So the first one's gonna be evaluated at 0, is that cool? Next one's evaluated at 3/4. Then, I forgot already, 6/4. And then 9/4. Let me stop for a minute. So like, this times this is the area of the first rectangle, this times this is the area of the second rectangle, so forth. Okay. So this is 3/4. F of 0 is easy to get, yeah? You could see it, you could do it. You can see it, you can do it. What's F of 0? 4. I love it. Now somebody help me out with what's F of 3/4? What is it from the function? 5.6875. 75. Neato. Thank you. F of 6/4 or 3/2. And you guys remember, if you want to, you can use the table. Plug the y equals. You could use the table. Is everybody with me? If you don't want to, or you forgot how to, just plug the shit in. It's fine. So yeah, what? I'm sorry. 6.25. And then F of 9/4. 5.6875. I like. Okay. Blah 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 blah. So then just throw all that in the old calculator. I'm not going to try to do it. I say that and I started. Huh?
16.249%.
Let me see. 15, 20. Oh, that's after you times 3/4, right? 16.209.
209.
All right. Is that what you guys are getting? Anybody else doing that? Everybody turn their calculator in, which is not the best idea, but it's up to you.
We got a different.
Different answer? Okay. All right, let's do this. What'd you guys get? 16 point.
21875.
Let's see, so 3/4 times 4 plus 2, 5.6875 plus 6.25. Real quick, how many 5.6875s do I have? Okay, so I'm just saving some time. 16.21875. Okay. You don't have to do 2. Everybody, you guys with me? Okay, so that's our estimate for what the area is. Would you put money on this being exactly right?
No.
Hell no. I'd put a lot of money on it being wrong somehow. Yes. We only use 4 rectangles. Even though these seem to fill each other in, they more than likely don't perfectly do that, right? Okay, I like it. Now, here's where we're going to do this stuff. And what I've done on this sheet, almost every problem in section 5.2 that wants you to use this process, you're going to do these exact steps. Okay, so. And it's kind of funny. It's the exact same kind of process we used here, just with less numbers, more unknown shit. What got us started up here? What was the first thing we calculated? The width. Okay. So now, how many rectangles am I using in there? N of them. So what's the width? It's always B minus A divided by how many rectangles I'm using. And how many did you just say I'm using? N. So the width is 3 over N. Why does it make sense? If N is 4, did we get 3/4? What if N is 6? Wouldn't that be 3 over 6? So of course the width is 3 over N. However many rectangles, it'll be divided by that. Okay, I like it. Now see if you guys remember what we're going to do next. I'm not sure why I did left-hand points, but I'll be okay. XI. Where do I start? Where did everything start when I was making rectangle? Yeah, 0, right? So if I start at 0, how do I get to the I-th rectangle? Who remembers this from yesterday? How big is each step I'm taking? How big is each step? No, we're not here anymore. 3 over N. Damn it. right? Isn't my width 3 over n? Isn't that how big of a step I'm taking? And how many of those steps do I have to take to get to the ith rectangle? I gotta take I of them, yeah. So it'll be I times 3 over n. So in general,
And why is it 0 plus?
where do I put it here? Because where do I start?
Okay.
0. And then, now, be careful. This is where people make a mistake. Do you see how this is 3i over n? Is xi always going to be this times I? No. This was nice because it started at 0, yes? So if I started at 1, this would be 1 plus 3i over n. You guys kind of with me? So be really careful. It's always got to, and please just let this make sense. How did I know to stop at 3/4 here? Because I started at 0 and I went this far. So I start at 0 and I go this far this many times to get to the ith one. Okay. Now, if you want to follow along on the sheet, you can see what to do next. But just to show you, I know, let me leave the limit out of it for a second. I need to analyze this thing before I can take a limit, right? I have to figure out what this is, and then I can take a limit. Are you guys with me? So the first part of this is just getting what I need. What do I not know yet that this needs? Do I know delta x?
Yeah.
Yes. Do I know xi?
Yeah.
Yes. Do I know f of xi?
No.
No? Okay, sure. So this happens so often in mathematics. You have a formula for what you need to get, and then you can just step back and go, what do I not know this formula needs? And then you make it. We've done that a lot of times already. So what do I still need?
F of
f
x.
of xi, okay. So somebody help me out. What would f of xi be? What is f of x? It's this thing here, right? So what's f of xi?
4 plus 3xi
I like it. Keep going.
minus xi squared.
Now, can somebody improve on that? Do we know what xi is?
Yeah. This is a 3i.
All right, let me stop for a second. You guys see the progression of this, right? Get delta x, figure out xi, shove that shit into f, right? So we're kind of doing it in 2 steps. You could have just put that in there, but this is good. Wherever I see an xi, I'm going to replace it with
3i over n.
3 over n, because that's what the hell it is, right? So I get 4, and real quick, just to show you, we're doing exactly the same work we did earlier. How in the world did we get a 4 there?
Because we plugged.
We plugged the first thing, and how did I get 5.6875 there?
Plugged
Because we
3
plugged the
plus.
next thing into the function. So isn't that exactly what we're doing? We're just plugging each thing into the function. That's all we're doing here. So before plus, what's 3 times 3i over n?
9i over n.
Minus, what's 3 over n squared?
9 over n.
Okay, stop for a minute. So this is kind of like the form we're trying to find all the pieces for, so that then I can put it together and then I can let the number of rectangles go to infinity. But I can't do this limit until I have something to do the limit of. So I first focus on putting this thing together. Okay. So again, just to remind you guys, real quick, this is not going to be our future. This is our moment. This is like the limit definition of derivative. We're immediately going to start making shortcuts for this. We're not going to always do this thing to guys. At the same time, I keep saying that, but of course you know I love this shit. This shit's the coolest thing in the world, but I understand that you might not feel the same. So I just want to remind you guys, this is not going to be like the next few weeks is this. Yes?
You also need to squared over n squared.
This year?
Yeah. We're doing,
Okay, so what does this need?
xi squared.
Yeah, and what's xi?
3i over n.
So what do you get when you square that?
9i over n squared.
Of course not. You square this, right? 3 squared is 9, I squared is I squared, n squared is n squared. Okay, I like it. How we doing?
Does that say x?
No worries. What sucks a little bit, I don't even know if I want to say this. I don't want to say it until somebody brings it up. Is everybody cool with this?
Yeah.
Alright, there's one little thing that could trip somebody up, but I don't want to say it because I might make somebody get tripped up, so I'm not going to say it. Okay, so now I can put this thing together, yes? So this would be the sum. F of xi, which is this, times delta x, yes? I'm just throwing the shit in. You guys with me? This happens so often. I create the shit and then I throw it in. What was delta x again?
3 over n.
3 or 4.
Through N.
Oh, 3 I over n.
Yeah, 3/4 is when I knew how many rectangles. Now I don't know. Yeah. Oh, I'm sorry. I'm looking at xi. Yeah, so this I shouldn't be there. You're right. So delta x is 3 over n. Like that. Thank you. Yeah, so my eyes went here and they should have went there. Okay. Okay, so now I've got that set up. I'm going to put the limit out front. I'm going to let the number of rectangles go to infinity. Okay. So I want to remind you about what we're doing. Is anybody disturbed about the work so far? Does it look, it doesn't necessarily look straightforward, but each little piece by itself makes sense. It's just that when you throw it all together, it starts to lose some meaning in your head, right? But this is just says, add up the heights times the widths. Isn't this just adding up a bunch of areas? These are every height and every width. So when I multiply, I get an area, and I'm going to add them up. That's the idea. Okay, I like it. So what I'm going to do now is I'm going to simplify this inside. What can I do? What's the only simplification I can do? Distribute.
Factor out a 9i over n.
Yeah, distribute. Do what now? I can't factor out an I and I over n because does S have a 9i over n? So no, I can only factor out something they all have, and they don't all have anything. So what do I get when I distribute?
12 over n.
12 over n,
27 over n squared.
27i over n squared, 27i squared over cubed. Okay. As per the usual, I have not given us enough room, but that's okay. You guys all have paper. Hopefully. The one nice thing about this is the process really doesn't change. You're gonna have different functions, right? You're gonna have different 0 to 3. It's not gonna be 0 to 3. It's gonna be 5 to 7 or whatever. But the process we're doing now is always the same, right? Okay. Now, let me see if you guys are cool with this. Let's see. Okay, let me see. I'm gonna date myself here, but back in the day when we had checkbooks, nowadays I think everybody just trusts the banks to do the right thing, but if you wanted to balance your checkbook, when you add up all your negatives, add up all your positives, and then combine those, yes? So do you see how this is what's this symbol mean again? It's the sum of these things, yes? So couldn't I add up all of these plus add up all of these? Are you guys kind of with me? I can add up whatever order I want to. You guys with me? So for example, nice concrete example, yes? If I had to add up 1 plus 2 plus 3 plus 4 plus 5 plus 6, if I wanted to, couldn't I add up all of the odds and then add that to all the evens? Would that I'd get the same answers if I added them? And of course you got the Gauss thing if you want to add it the first to the last and do that weird shit, yes? Okay. So what I'm going to do right now, it's going to look like I'm distributing. I'm not. Because this is not this times this. This is the sum of this. But how do I add stuff up? Well, I can add up these guys by themselves. And then I can add up these guys by themselves. Oops, and then I can add up these guys by themselves. Does that make sense? If I have a big ass list of things to add up, I can add up any chunks of them I want to. And then add all those chunks together, right? Okay, so in your head, if you wanna look at this as if a distributed, don't even do that, I don't like that. It looks like a distributed, doesn't it? We all know better. Cause this ain't sum times this shit, this is sum of this stuff. Is everybody cool with that idea? What's the only operation in this whole thing? Addition. What does that mean? Add. These are add. Subtracting is adding the opposite. So this is all addition. I can add whatever order I want to. So I want to add all these things, and then on top of that I'm going to add all these things, and on top of that I'm going to combine all these things. Okay. Now, see if you guys are cool with this. Do you all understand? What would the first three terms of this be? What's the first term of this? What's the first term? 12. What's the second term? 12 over 2. What's the third term? 12 over 3. You guys kind of with me? So doesn't every term have a 12?
Yes.
Any constant I can take out. That's just the equivalent of GCF. Every term I'm adding has a 12 in it, correct? So I can just take a 12 out. Does every term have an N in it? Yes. So let me see. I gotta back up because I'm just too close to this. It's not N that's changing. That's my bad. It would be I that's changing over here. So every term here would have a 12 over N in it. So let me do this a little more carefully. Little side note. Don't even write this down. N is not what's changing. That is my fault. Sorry. I is what's changing. So when I is 1, isn't this 12 over N? When I is 2, isn't this 12 over N? When I is 3, 12 over N? Okay. Now, so what I can do for this piece right there is I can take a 12 over N out. And what's left if I do that? 1. Okay. So we'll talk about that in a minute. This is what I was talking about yesterday about the summation sees I as a variable. The limit sees N as a variable. The limit is letting N change. The sum is letting I change. Okay, so what's the only piece of this guy that I can't take out? I is the only piece I can't take out because I isn't always I. It's 1 and then it's 2 and then it's 3. So I can take out 27 over N squared and I have I. Of course, same thing here. What's the only thing I can take out? What's the only thing I can't take out? I squared, kick ass. So I can take out a 27 over N cubed. And again, the nice thing is, when you're doing these problems, and you're not going to have to do a bunch of these, the math is the same. Everything I'm doing now, you will do. You're not going to have the same kind of like numbers and so forth, but the same idea. It's exactly the same idea. Now help me out. Look back at the other side of this paper. See here? What is the sum, and real quick, why does this make sense? If I add up 1 7 times, what am I going to get? 7. If I add up 3 12 times, what am I going to get? Holy shit. So if I add up a constant N times, I'm going to get C times 7. I'm going to get NC's here, yes? So this sum, what do you guys tell me? If I add up 1 N times, what do I get? No, if I add up 1 N times, 1 plus 1 plus 1 plus 1 N times, I get N. Does that make sense? Okay. So you can either look at that as something to memorize. By the way, I'm going to give you these. Don't freak out. Sure. If I add up 5 10 times, what do I get? If I add up 10 5s, add up 5 10 times. Right? 5 plus 5 plus 10 times. What do I get? 50. Yes? So if I add up 1 N times, I get N times 1. Okay, good. Now, here, 27 over N squared. What is the sum of I? And again, look at it. Okay. What is the sum of I? Look at it. You don't know, but now you do. Yes? It's this, yes? Remember, what was this again? Where'd this come from? Nerdy ass little Gauss showing his teacher up, yes? Saying, I got you and your add this shit. I got you. So that's what this is, yes? Yes?
Remind me where the n and the other one came from again? 12 over n, and then it has the n right there. Where did it come from again?
Alright, so,
Sorry.
okay. So,
Just real quick.
if I had a list of 12 ones, what will that add up to be?
12. Wait.
So if I,
Yeah.
yeah. If I have 12 ones adding, what does it add up to be?
12.
12. If I have 38 ones adding,
38.
so if I have n ones, which is what that says, how many ones does this say I have? N, yes? When I is 1, this is 1. When I is 2, that's 1. When I is 3, that's 1. So how many ones do I have? N of them. So if I add up n ones, of course I get n.
Okay.
That rule is straightforward. That makes all the sense in the world. The next rule we had to talk about. That's the Gauss thing, right?
Yeah.
Okay.
Thank you.
And then the next rule, I ain't got time to talk about, so I'm sorry. It's too bad. You're just going to have to accept it on faith. But that's what the I squared is. And you guys see that's going to be here, right? Excuse me, n plus 1, 2n plus 1 over 6. Now, just to remind you what I just said, I will give you these, yes? I will give you those formulas for the sums. Okay. So now do you see this whole thing we're doing from a different standpoint? If I can get all of these down to i's or I squares in there, I can then replace them with those formulas. I then know what they are. So that's why I'm trying to get all the other shit out of the way. I'm trying to get sum of I squared. Okay. I love you guys. I see on your faces you're all like, start making sense. We're almost done with the semester, so I'm sorry. I'm not going to start doing anything new. So what happens here? Was cancel? Nothing much. Now watch this. Watch this. Let me see if you guys can hold this. In fact, what's the limit as n goes to infinity of 12? 12. Okay. Look at this. Let me see. Come on, you guys are really good with this shit. What's the limit as n goes to infinity? What's true about these n's? What's the degree of the top? And what's the degree of the bottom? So what's the limit of this piece? No. The top degree is?
Positive.
What's the top degree? No, come on. What's the degree of the top?
2.
Second degree, yes? Does everybody see that? N times n. Don't multiply it out, but you can see it's squared, yes?
Yeah.
Second degree, what's the degree of the bottom?
Second.
Second degree, what's the limit letting n go to infinity if they're the same degree? The ratio up there, so that the limit of this piece here is 1. And then you have a 27 over 2 times 1. Do you see that? So what is this limit caring about? N. So I can kind of focus on the n shit. Let these kind of so the limit of this thing, watch how I can write this. The limit of that thing is 1. So what's left over here? 27 over 2. Next piece is a minus. Looking at the ends again.
3rd. Over 3rd.
What's the degree of the top? Does everybody see it's a third power, yes? Don't multiply the shit out. No reason. I can see it's 1, 2, 3, n cubed. What's the leading coefficient though on the top? 2. Bottom is 3rd degree. So what's the limit?
2. So number 2.
Don't worry about these. What's the limit of this?
2.
The top is a cube. What's the leading coefficient?
2.
2. The bottom is a cube. The leading coefficient is 1. What's the limit of this?
2.
2. Good. Okay. So then what do I get here? 54 over 6, which is? So then I get whatever that is. 33 times? Is it 16.5? 16. Oh, look, guys. So this is 3. 3 is 6 over 2. 6 plus 27 is 33. 33 divided by 2 is 16. I'll just do it.
Not here.
Hmm?
Not here.
Yeah. What was our estimate? Remember, we did this problem, but we got an estimate for it. What was our estimate? Yeah. This is the exact answer. How do I know this is the exact? And why do I know this is most likely wrong? Because we only used 4 rectangles. Why is this perfectly right? We used a freaking infinite number of rectangles. Yes. Does everybody agree this work is a little involved? You know, like I disagree with the word little, but it's adding up an infinite number of rectangles. Yeah, I'm going to expect that to kind of look gross. This looks better than you would think. We're going to add an infinite number of rectangles today, kids. You know, like you wouldn't expect it. You would think it'd be just going forever, but no, bam, we did it. Okay, maybe, yes.
Will we?
What?
Will we be able
I really
to?
misheard you.
Will we be able to use this trick in our homework?
This is not a trick. This is like the limit definition of derivative.
Well, the trick you're going to show us, can we use that in the homework?
Not in section 5.2, because we're going to learn the trick in 5.3. Yeah. Yeah. Yeah.
Can you explain the correlation between the formulas again? So you only have to look at the power of what the numerator is.
All right, so let's focus on that for a second. Limit n goes to infinity of 4n to the 4th minus 6n squared plus 2 over 2n to the 4th plus 7n plus 1. What is that limit? You don't have to do L'Hopital's, right? We did this shit. This is from pre-calc. So really I'm asking what's the horizontal asymptote of this. So are the degrees the same? So therefore the limit as n goes to infinity is equal to the ratio of the coefficients. That's all. That's it. So let's try this one here. What do you mean same? No.
4 and it's a
Oh, okay. So the degrees are the same.
15 over
So you look at the coefficients.
Good. So what's the leading coefficient at the top? If you multiplied it out, you never have to multiply this shit out. If you did, what would the leading coefficient be? 15, right? 15n to the 4th. You with me? Does everybody see that?
Can you explain that?
If I did multiply all this shit out, if I just focus on the highest powers I would get, do you agree with me if I did these, I get an n squared?
Mm-hmm.
Do you agree with me if I then did this too, I get a 3n cubed?
Mm-hmm.
Do you agree with me if I then did this also, I get a 15n to the 4th?
Wait, you mean square?
3n cubed. So, would you agree with me? This would make n squared.
Times 3.
Some plus some shit, yes? And then if I multiply this, I'm gonna get 3n cubed.
And then
Okay, alright.
5 into the 4th.
N squared times 3.
Oh, okay, the
I
answer
got
to that.
you.
Yeah, so if I did multiply these out, I get n squared plus I don't care. If I did then multiply these out, I get 3n cubed plus I don't care. If I then did multiply these out, I get 15n to the 4th plus I don't care. Okay, good. So how can I see this really quickly? 3 times 5 is 15. The degrees are the same because I got 1, 2, 3, 4 n's, and I have 4 n's. So the top is 15, the bottom is 8. So the limit is 15 over 8. Okay. So coming back to the one we did, you see how there's a 2 on the top? 3 n's. 1 n cubed, same degree, 2 over 1. That's why it was a 2. Okay, I like it. And the nice thing is, this part's always going to look like this. It's always going to be a 2 here, right? Because that formula is set right there. See that? Okay. Blah, 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 blah. Oh, okay. So we saw that this was really close to our estimate. Now the one part, let's do this bottom, this last problem. what is the antiderivative? Now, there's no reason you would expect this to have any connection to what we just did. So just to kind of cut to the chase, we got 16.5 here, right? After all the work we did in the other paper.
Yes, sir.
What is the antiderivative of this? First off, what would I put here if I'm doing the antiderivative? Get gas. Big ass F. All right, go for it. What's the antiderivative? 4
X.
x. You can do it. It would come from an x. No, careful. No. That number doesn't tell us shit. Constants are our things. We do things. What tells me is the function part, right? What's the current power on the function? So where did it come from? Second degree, yes? The constants just sit there and take whatever the hell happens to them. So watch it, watch. So if I know this comes from an x squared, see if you guys can get this. 3 over 2, exactly. And so what would this be? It would have come from a cube, right? But a 3 would have come down. There is no 3, so there must have been a 1/3 there. One more thing. Okay, so let's do this. Here, I haven't developed this rule yet, but do you remember the rule for derivative of the core sheet? What's the derivative of this? Okay, so let's develop an antiderivative rule for, so let me write it like this. I want to figure out what big ass F is for x to the n. So, somebody tell me, if currently the power is n, what would it have come from that the derivative would make it that? N plus 1, is that cool? Because thinking backwards, I would have subtracted 1, so it must have been n plus 1. Holy shit, what's this here, Jeff? I don't know why I did this. Down. So this would have been x to the n plus 1. If I took this guy's derivative, what's the first thing that would happen? That would come down, yeah? Is it there, though? Okay, I really want this to make sense. This cannot possibly be this guy's antiderivative. One thing, there's no plus, but more importantly, it would need an n plus 1 out front, and it doesn't have it. So what must have been out front then? That is the rule. So here's what's really cool. Look what this does. I multiply by the current power, and the power goes down by 1. Is that cool? That's the rule. What's the rule for the opposite operation? I increase the power by 1, and I divide by that new power. I do the exact opposite of what I did to do the derivative. How should the antiderivative work? The exact opposite as the derivative does. Yes? So this one multiplies by old, and the new is 1 less. This one, the new is 1 more, and I divide by the new. Everything is opposite. That's why it's the antiderivative. How are we doing so far? Yes.
Does that say 1 over n plus 1?
Yes. So a shortcut way to write it, not really, but you just put x to the n plus 1 over n plus 1. Is that cool? So again, if I had x squared, what would its antiderivative be?
1 over 2 plus 1.
Yeah, the new. So what I always do is make the new power first, and then divide by it. Bless you. Okay. All right. So let's try a nifty one. Let's try. What if it was x to the negative 11/15? What is big ass g?
Plus 15 over 15.
Yes. So then you start with what the new power is. So here's the cool thing. Remember when you take in derivatives, I told you to subtract things? Does anybody remember that?
Yes.
So if I took a derivative of this, it would be negative 26 over 15. And that would come down. When you do antiderivatives, you add the damn things. That makes sense. If I'm doing the opposite, I'm going to do the freaking opposite. So what's negative 11 plus 15? 4. That's the new power. And then I do what with the new power? I divide it. But when I divide fractions, I actually multiply by the? So out front I'm going to put what? Let's see why this makes sense. If I took this guy's derivative, wouldn't the 4/15s come down? What's 4/15 times 15 fourths? Frickin' 1. That's what's supposed to be there. And then the power would go down by 1. Okay, maybe. So that is a rule that we've done problems like this. We didn't need a rule, but there's the rule. Okay.
What if the x had a coefficient in front of it already?
Oh,
How does that work?
I like it. See, that's the kind of stuff I live for. Anytime you want to, if you're like, this guy's doing shit that's too easy, let me get it, yeah, just ask. So, what if I had, let's make one that's not too crazy. 7/2, look at what I'm doing as I said it. X to the negative third. Sorry. What would big ass F be? So what I would do if I were you is I'd write the 7/2, and now I can focus on this guy. What would the new power be? Yeah, it's got to go up by 1, right? So -2. And then I do what with that new power?
Put 1 over the power?
Yeah. You guys with me? Okay. Yeah, -7 of course. X to -2 plus C. Bam. If you're ever not sure, what do you do to check yourself? Check yourself. So if you bring the -2 down, that makes it positive. It cancels, makes it 7/2, yes? And then the power goes down by 1. And of course the C dies. We kill the entire C. Poor little dude. Okay. How you guys doing? So it kind of makes sense. If there's a rule for power rules for derivatives, the antiderivative rule for that should be the exact opposite. Instead of subtracting 1, I add 1. Instead of multiplying by the power, I divide by the power, right? Okay. All right, so coming back to this, what is f of 3?
4 times 3 is 12.
Sure, 12 plus,
27,
good, 9 times 3, 27 halves, minus 27 thirds, yes? Plus C, is that cool? All right, and that's whatever. Well, let's see, what would that be? 12 minus 9, 3 plus 27 halves is 33 halves. What is f of 0?
0. Or C.
C, 11.
Did you put 33 times?
I think I did, yes.
Um,
Because that's what it is. What is f of 3 minus f of 0? What cancels if I subtract? Oh, sorry, I left the plus e out. What, if I subtract these, what do I get? If I subtract these, what do I get?
33 over 2.
33 over 2. Isn't that the answer we got up here? All right. There's no reason we would expect the antiderivative to somehow be related to the area. This is nowhere near a proof. This could just be coincidence that I got the same answer. What's that? Some of you guys look very perturbed. What's going on? All I did was plug a 3 in, and then I plugged a 0. That's all. And then if I take the difference of these two, the C's cancel, yes? I happen to get the same answer I got there. Now today we're going to prove that that always happens. We're going to prove that today. Now real quick, do you want to do this process every time you have to find the area under the curve?
No.
Do you wish you could just do this much work? Do you understand how we got the same answer we got there in this much work instead of in, oh shit, where'd my paper go? Well, the whole frickin' paper that we had a second ago, yes? You guys all with me? Okay, now, I love, Stephanie's over there going, that would be nice, dude. But why the shit would that be true, right? Or maybe you wouldn't say shit, I don't know, okay.
Yeah.
I would, I'm sorry, I say shit a lot. Okay, yes?
I can't read your writing at the bottom. What is
No
that?
way.
It's-
Um,
it says, what's it called? F of 3 minus F of what? F
F of 0.
of 0?
Oh yeah, sorry. Yeah, there you go. Okay. Just doing what it asked me to do. Yes? Okay. I get excited about an idea and I don't focus on my writing and I apologize. Okay. Alright. So let's do this. We are going to develop the connection, and I need you all to be a little motivated to do what we're about to do, or else I'm gonna make you do this every damn time. Right, and I don't want to make it sound like I'm threatening you, but I'd much rather have a shortcut method rather. In fact, you all remember this is not all the work. The work is somewhere in another sheet of paper. The entire freaking sheet of paper was the work. Here, there. That was the work, starting up there and then going down to there. That was the work, yes? Now compare that to this. So we are hoping that this is not just a coincidence, that I can just do this all the time instead of all that shit. Are you with me? By the way, you guys all see why I picked 3 and 0, right? Where'd those come from? Yeah. I want to go from 0 to 3, yeah? So if that would have been from 1 to 5, I would have just done f of 5 minus f of 1, yes? So, again, there is currently no reason for you guys to believe there is a connection between antiderivatives and areas, except for the fact that I said so. And you're like, I don't know, man, you could be making all this shit up. You'd be right. Every day I make this stuff up. You guys just don't realize. Okay. So let's do this. So everything we're about to do right now, yes?
Just a quick question.
Yes.
What is the quiz about tomorrow again?
4-9.
4-9.
Antiderivatives. 4-8 is going to be on the next test, but I want to give you guys some time to try it out. Antiderivatives we've sort of been doing the entire time, really. So I'm going to focus tomorrow's quiz on antiderivatives.
So just 4-9.
Just 4-9. Yep. Okay. All right. So again, just to remind you guys, we want this shortcut. We're going to have, everything we're about to do is going to be getting to that shortcut. And the first step to get to the shortcut is to define a new function. And you're all like, oh, that sounds great. Using something we kind of already know. So let's do this. The process of finding the area under a curve is this here. Yeah, they're in. Yes.
Sorry, is this still 5-2 or is this 5-3?
This is 5-3 now. Okay, thank you. And this is on some interval a to b, yes? Because, and that's how we define what delta x is. Is everybody with me? So this is the process to find the area under a curve from a to b. Is everybody with me? Just to point something out that I haven't said yet. If my function is this, do you see how my area would actually be negative? Which is actually absolutely fine. It is fine to have negative area because this area means something physical. So like, if it's up here, that could mean profit coming to me. If it's down here, that could mean profit going away from me, like I'm paying money. So if my entire function is down here and I get the area, that could represent the entire amount of money I lost. It's negative because I lost freaking money. Now in general, if you say there's negative area, something's wrong with you. But this area represents a physical concept like profit, and can profit be negative? Oh, hell yeah. Okay. Maybe. Okay. So, I want to introduce some notation. And actually, one of these things I've already talked to you about. We saw it in the calculator and I pointed it out. Remember, this is sum. So we use a Greek letter E, so now let's use a S for sum. You guys remember this? And if I let the number of rectangles go to infinity, what they decided to do was they took an S and they just pulled it. So it becomes this symbol here. So this is kind of like the evolution. This entire thing, we represent it as an infinite sum. That's what this elongated S means. It's an infinite sum. Let me say this again. This elongated S symbol represents infinite sum. So I'm kind of just shortcutting the amount of shit I have to write. All right, next thing. What happens to this dude when the number of rectangles gets really, really big? What was delta x again? B minus a divided by n. So if I let n go to infinity, what is happening to delta x? It's getting stupid small. That delta symbol is for crude steps. When I make it infinitesimally small, and the limit that n goes to infinity, isn't this going towards 0? Does it ever get to 0? No, because the n never gets to infinity. So it gets so stupid small, we're gonna represent it with something different than the triangle. The little triangle dude means like a crude step, like you skip a lot of shit. If I let the number of rectangles go to infinity, am I skipping any numbers when I move? I am hitting every single possible number. I'm not skipping anything. If I go from 1 to 1.01, did I skip any numbers?
Yeah.
How many? An infinite number of numbers. So if I let the number of rectangles go to infinity, my width goes to infinitesimally small, I don't skip a damn thing. So I can't use delta, because that's supposed to be for like skipping shit. That's big steps. So what that symbol becomes in the limit is dx. Instead of delta x, it's dx. So when you see dx, that means an infinitesimally small change in x. Now, we've seen this shit before. What was the first thing we did with calculus was we said, what's the slope at this point? So what do we do with this distance? We let it go to 0. So we've talked about infinitesimally small distances on the x-axis. This is the symbol we use for it. And this guy is just f of x. Because now it could be every x value on the x-axis, not just some. You guys with me? Real quick, let me see if I can make this make sense. So if I do this rectangle, yes? I could pick the left endpoint or the right endpoint or the midpoint. You with me? If I make the rectangle go infinitesimally small, then am I skipping any x? Wouldn't the next rectangle start immediately? So it would be every single x value. So we just say x. It's every x value on the x-axis. It's not just certain ones. Okay, I over-explained that, but it's okay. And then here's how I represent this shit. Do you see how this is absent here? If I just put that, could you tell what interval I'm talking about? No. So what we do then is we put on the endpoints of this, sort of like we do here. We're going from A to B. So this entire symbol, let me write it again. This says sum up the function values from A to B. And how does it do that? It uses an infinite number of rectangles to kind of do that. Do you see how this part, f times delta x is there, and this whole thing is the infinite sum. Okay. So let's do this. I'm going to do a problem out of the book. Concrete frickin' problem. Please, you got Jeff. Okay, I got you. Let's see, 5-3, or is it 5-2? 5-3. Yes, 5. All right, look at number 3. Okay, let me move up here. Let me put this up a little bit. Screw their questions. I'm probably going to ask their question. I don't care. What would this mean? All right, cool. Now use less technical language. When I add up an infinite number of rectangles, I'm finding the area. Sweet. So now use that. What does this mean? Area under f from 0 to 1. So what does that equal? You can do it.
2.
Yeah. So isn't the area under this from 0 to 1, isn't it just that rectangle? 1 times 2. So it's 2. Are you guys with me? That's just 2. So what if I want to know this? What do you got, Jeff? Yeah, sure. What do you have to be careful about with that? That's the area under f from 1 to 2. From 1 to 2, what do I have going on? I have a triangle, and I have a rectangle. We already know this rectangle is 2, yeah? Area 2, are you with me? So now I just got to figure out the triangle. And of course, the triangle is going to be exactly, let's see if you guys can see this. Isn't it half of this? You guys see that? So it's 1. So then what's this answer? 3. Okay. You guys see that? So of course they're going to give us some that's why I love, I like progression of stuff. They start off with shit that we know the geometric formula for, so I can just really solidify that this symbol means area under the curve. Okay. So Now that we understand that symbol, let me make the function they're actually talking about, because they have a function here. Okay, let's not look at that. Hold on. So this symbol, these symbols mean area under f from a to b. I'm going to make a function that uses this idea. So for example, like, what's the idea of sine of pi over 6? What's that idea? Can somebody tell me the idea of that?
The y value.
The y piece,
Where
where the angle is
pi
5
over 6.
or 6 radians, right? And then we make a function out of it, correct? I just shove an x in instead of a number, and then it's a function all of a sudden. Are you guys with me? That's how we can create any function. I want to first know what does it do to numbers, and then I can just shove an x into it, and then I can start graphing it for an infinite number of numbers. Are you guys kind of with me? That is a drunk history of algebra right there. Okay. So I'm going to do the exact same thing here. I'm going to shove an x there. Now, see if you guys are cool with this. So far, I'm going to continue writing in a minute, but I really want you to be on board with what's about to happen. When I was doing like position, does anyone know what this would normally be? No, I'm sorry. So like I can have f and I can have x here, right? F of x and x. Or I could have like velocity, time. There we go, right? So this axis does not have to be the x-axis, does it? X is just a random letter we use sometimes. You with me? I really want you with me. Okay, here we go. I want this number to be a set number, but I want this function to do what it does. So what I really want to do is I want to have a function. I want to start at A, and then I want somebody to pick how far they want me to go. So just like I was doing a second ago. So if I start at A and then somebody gives me a value for this, then I know how far to go. If I let this also be X, what the shit? I can't let X do multiple things all at once. I don't know if you guys are really, really with me here. So this function, all this says is, give me a function, give me a starting point, and then tell me how far to go, and I'll get the area. So what changes in this expression? What can I change? Which variable? X. I can change X. The function is given to me, but I can change how far I want to go. Are you guys all with me? That's another reason why we put a different variable here, to make it really clear that that is shit I can't do anything with. I can only change how far I can go. Are you guys with me? Say again? Right here. So real quick, you guys were really cool just a minute ago with this stuff. And again, you guys have to remind me to erase that, I'm sorry. But it's kind of nice this is still there. You all understood what this meant. Start at 0 and stop at 1, correct? Couldn't I change the beginning and the end numbers? Couldn't I have kept this to be 0 and made this 1, 2, 3? Okay, so can't I make this some number and then let this one change? That's all that is. That's all that is. So if I'm given a function, f of t, and it does stuff, yeah, and I have a position that I start, then somebody can come along and say, okay, I want to know the area. So g is the area function, because it's equal to the interval, which is the area. Oops, I just said a word. It's equal to this. Well, I can use that word. This is called the interval. This here is called the interval. Just this poor little name, which represents the area under a function. Yes, okay. So, I'm given a function, I'm given a starting point. I get to pick how far to take it. So I get to pick if I want to go there or there or there. And of course, what I pick changes how much area there is, right? So let me ask you one straightforward question. So if I have a function defined with an interval, right? So here it is, function, yeah, A And I can go as far as up as I want to, yes? Oh God, I really hate overheads, but I'll be okay. Don't stop working, I'm sorry. What would I get if I went to A? So where am I starting? And I'm going to, how much, no. Wouldn't this be this? How much area do I get if I start here and I stop here? Beautiful, I love it. That's 0. Of course it's 0. There's no width then. How could I possibly have an area if there's no width? Are you guys with me? That's one little thing to notice about this function is, if I plug that value in, I'm going to always get 0 because I'm not going anywhere. I'm not picking up any area. So one way to look at this function is, as x increases, I'm just kind of picking up area as I move along, yes? Okay, I like it. Okay, let me stop for a moment. This is really trippy for several reasons. This symbol is still relatively new to us, and we've never seen a function quite defined like this before. We've never had a freaking process represented like this before. Okay, so is it relatively cool with that? So really, this problem, I wanted to give you a concrete example before I talked about this, but to be honest, this problem we just looked at, now you can kind of see what it is fully. They tell us that g of x is this, yes? So they tell us we're always going to start at 0, but we get to pick, or we get to be told where to stop, yeah? So we just did g of 0, yes? We did what would g of 0 be? We didn't do that, but now you can do it. What would g of 0 be? 0, because I didn't go anywhere. I didn't pick up any area. G of 1 we did. That was the little rectangle. G of 2 we didn't really do. We did G 1 to 2, right? But G of 2 would be the area we got for this plus this area. Do you guys see that? I like it. So again, G of 2 would mean go from where to where? 0 to 2 and get all the area that you can. Are you with me? What's going to happen up in this region? That area is going to be negative. So if I went from 0 to 5, I'm going to start to lose area right here. Does that make sense? If this was a velocity function, this is my velocity. I start at home. I'm getting further away from home, correct? Because my velocity is positive. Are you with me? What happens right at this point then? I turn around, my velocity is 0, now I'm going negative velocity, correct? So shouldn't, if I, here's a really neat thing. Okay, let me see if you guys are cool with this. Oh shit. Yeah, Jeff, you have erasers. I have my own eraser. So I'm saying if this was velocity and this was time. What was I about to do? I forgot. Shoot. So what would the, how do I say this? When I do an area, what units is this? We'll say hours, right? So time. Are you with me? Hours, for example. What units is this? V, which is what? Like normal, every day. You drove here today, you went how many, what's what? Miles per hour. So do you see how if I get the area, what units will that be? Miles. Do you guys see that? That's kind of cool. It's one of the immediate things about this idea of integration is they actually multiply the units because I'm getting areas, right? So when I get an area of 2 here, that could mean I've gotten 2 miles away from home. So I'm getting further away from home all the way until here, because that's where I turn around. So doesn't it make sense that once I keep going, now this is going to subtract from how far I am away from, because aren't I starting to go back to home?
But it's not negative. It's just less.
It is negative.
It's just less than. It's not negative.
It is negative. So what is the area from, what is this, 3 to 4? Negative, because it's below. I like it. Okay. So is it a physical negative area? No. But do you agree with me, if I turn around, somebody leaves, they're adding to the distance away. If they turn back, aren't they taken away from the distance they're away from me? So that's what the negative area can be negative if I realize what physical property it's talking about. Again, can profit be negative? Yes. Can the distance you're getting away from me be start to become negative? Yes, because you could be coming back towards me. Yes? Okay, maybe. All right. If you go up to this point, you will have gained so much distance away from me. What's happening after that? Is it adding to it? No, it's subtracting because this is freaking negative. Okay, that's lots. All right. So again, it's not a physical negative area. Quantities can be negative, so that can be represented here. Okay. Yes.
So to find 3 versus G of 3, would that be 2?
G of 3 is right. I hate when they don't label all the things 1, 2, 3. Oh, it's here. So then you have to find. We already found this area. That was 5, right? So then you just have to add this big ass triangle.
Well, in that itself, that triangle, would that be 2? And then you add.
So that'd be 1 times 4 cut in half.
So 2.
Yes, 1/2 the base times 9, so it'd be 2. So that'd be 7 total, yeah?
Okay.
You with me? So G of 3 would be 7. Is everybody with me? Because how much area have you picked up? 7. So if this was velocity versus time, we will be 7 miles away from home at this point. Then I say, oh shit, I forgot my freaking backpack. So then I turn back, yeah? Then I start losing distance from home. So of course this has to be negative, so it takes away.
So G of 4 would be 7 minus 1/2.
Good, 7 minus 1/2, kick ass.
But that's still positive.
Sure, the end, but if I go far enough, can't I go past my house the other way?
Yeah.
Okay. This area is negative. The overall area would be positive because when I subtract it, I end up with a positive number. Okay.
But even if you go past your house, like you're going past your house.
Yeah, but again, in physics, we define one direction to be positive, one direction to be negative. So then we'd be gaining like negative, but we're not going to go all the way there. We don't need to. Okay. I'm with you, though. All right. Now, some of you guys are still like, how does this relate to antiderivatives? Okay, we're getting there. This is one piece we need. We're about to do 2 things. We're about to do 2 parts of a theorem, and the name of the theorem is the fundamental theorem of calculus, which I affectionately call FTOC. So we're going to have FTOC 1 and FTOC 2. It's going to be 2 parts of this thing. So there you go, some emphasis. Do you think this is important? It's called a freaking, I want to put another F in there. The freaking fundamental theorem of calculus, the FTOC. Okay. This is going to undergird, I like that. Everyone. One of the 2 parts is much more important, but the other part, the part that's important, could exist without the first part. So we're going to talk about both parts. We're going to use the hell out of one of them, and the other one you're going to forget, and it's going to come up in Calc 2, and you're going to be like, I forgot this shit. So I'm going to try not to let that happen. Now that we've got the idea of this function set, let me ask you this. What was the entire first part of calculus basically all about? Well, no, that was not the entire first part. That was like the first week. Part of the first week. What was the entire first part of calculus? Derivatives. So we said, okay, what's the derivative? Trig function. Oh shit, so we did that. What's the derivative in natural log? So we did that. Do we have a new function? So what are we going to do to it? Take its derivative. I love it. Okay. All right. This is so cool. Just stay with me. Don't freak out. What we're about to do is nothing you're ever going to have to necessarily directly do, but I'll show you the kind of problem related to this. We're going to take the derivative of this thing in general. We're finally going to connect our shit to antiderivatives. We're about to do that. This. I'm always so hopeful that I do a good job with this shit, because this is some cool shit. So here we go. So here's f of t from a to b. Actually, I'm sorry, from a to x. There we go. So this is g of x. So this function is weird, because have I graphed g? Is this the graph of g? No, this is the graph of f. Where's g in this picture? The area. So that's another reason why this function is trippy, It's because the graph we normally draw is not a graph of G. Where's G in this picture? It is the area. You guys with me? So that is one level of this that is definitely trippy. Okay. So if I want to investigate the derivative of this, what's the limit definition of derivative say? So if I have a function g of x, just forget what it is. How do I set up the limit definition of derivative? Don't worry, we're not going to do a bunch of shit with this. You're not going to have to do a lot of this. Just for right now. Here we go. Somebody remind me, for g of x, how do I set up the limit definition to get the derivative? G of x plus h over h. And that would be g prime, yes? Is that cool? Everybody agree? Okay. Especially since I just said you're not going to suddenly have to do a bunch of this again. Okay. So watch this. This is so cool. This is g of x, correct? This area in here. How do I get g of x plus h? What's the h mean again? Is h really big? Because what am I going to do with h? Let it go to 0. And isn't it, so g of x plus h, can anyone tell me, where would g of x, how far would it go? This is g of x. How do I represent g of x plus h? Don't I just go h past this? Is that cool? Oh, I love you guys. This is g of x, you guys agree with me? Alright, let's do this. Alright. If I have f of t, and I want to represent g of x, I would go up to x, correct? How would I represent g of w? I'd go up to w, yes? How would I represent g of w plus c? I go up to w plus c. Okay. So how do I represent g of x plus h? I go up to frickin' x plus h, right? So this is doing whatever the hell it's doing. You guys with me? Alright, let me stop for a minute. Because what does the top of this need? The difference in those, yes? What does the g function do again? It's the area. So isn't this the difference in two areas? So that's why it's a very visual kind of proof here, because it's all about the area, not just the base. Okay. Does everyone agree that one way to represent the area here would just be to do a rectangle like we've been doing? And what am I doing with h eventually? What am I letting h do? Go to 0, right? So doesn't it make sense to let the height of this be related to this? Because I'm kind of like squeezing just to only be that anyway. Are you guys with me? So how tall is this rectangle? So, does it make sense to let the height of this rectangle be governed by x? Because I'm going to let h go to 0, and that's the only thing that's going to be there eventually. Here's x plus h. I'm letting h go to 0. So what's the only possible thing that could be the height would be at x? Are you guys with me? So it makes sense from the beginning to let that be the height. I'm kind of doing the left endpoint. I'm letting this be the height. Because this is going to become that. Yes? Alright. So how tall is this rectangle? No, I'm going to let this determine the height. This is x. Whoa! What's the height? You can do it. If I know the input, how do I get the output? F of x. Okay, so this is f of x tall. How wide is it? H. Is that cool? You see that?
Yeah.
Okay. I know, I'm with you. So what's the area of this rectangle?
F of x times h.
Yes, h times f of x. I like it. You guys all with me?
The area is h times f of x.
Yes. Does that make sense? That's the width times the height. Can't beat that. Right? Okay, I love it. So, remember, we want to get to this stuff. What is g of x plus h minus g of x. You can do it. Here's g of x, correct? Here's g of x. And this is g of x plus h, all the way over. So what's their difference? It's an area, correct? So what's the difference between this area and this whole area?
Excellent, that's what, if I say.
I love it, give it.
So isn't, if I take this area and I subtract this area, aren't I left with this area? And we just said what this area is, didn't we? Okay. If I subtract this whole area minus this area, this is g of x plus h, yes? And this is g of x. If I subtract them, I get the bar. I get this rectangle, which is hf of x. So this will be h, Jeff, you can do it. And I'm letting h go to 0, yes? Okay. It's a little loosey-goosey, but I don't have time to be specific. See how we divided both sides by h? No, not sure. Can I divide both sides by h? Yeah. What is this? So what? How can I represent that? G prime. And what's over here? Yeah. So let me really make sure you get this. Okay, this is almost equal. This means, all right, let me let you guys write this down. Let me summarize what we just did. So everybody got what they want from that? Yeah? No? Okay, and again, this is all derivation, you don't have to do again, but if I define g of x to be a to x f of t dt, the derivative of that is just f evaluated at this endpoint.
Is that an FT?
Say it again, sorry.
FT at the top?
Yeah, of course, yeah. The way it's been since we started talking about this. So help me out. How would you represent what I want to do now? So I took a derivative of both sides to get here, correct? Now I'm about to do something a little weird, but we are there, everybody. How would I represent this side if I took its antiderivative? Big ass F, yes, thank you. Now, be really, what's missing?
Plus C.
Big ass. Now, if I took the antiderivative of this side, I better take the antiderivative of that side. Can everybody see this is not big ass G? Yes? Why is this not big ass G? Because it ain't G. So what's the antiderivative of the derivative of G? G. So, watch this. This is so weird. Okay. Now, understand, right now, you're not entirely certain. But do you see how basically we just related these two things? Isn't G this and G is somehow this also? Yes? You guys kind of with me? So let me make this cohesive. So, before I forget, I said it and then I never really said it. This here is the fundamental theorem of calculus part 1. If I'm given an integral function, the derivative undoes the integral, which by itself is evidence that the integral is the antiderivative. But then I do this. I take the antiderivative and then I really see it is in my face. G, which is the integral, is equal to the antiderivative. They are directly connected to each other. So the last thing I got to do is this. Let me see if you guys are cool with it. If I have this, okay. Oh, let's see if I can. All right. Do you all agree this would be? Let me see if I can say this. I don't know how to say this. All right. Visually, this would be 0. This would be A. This would be B. So this would be this area here, correct? Now go. What's G of B in this picture? What is G of B in this picture? That's a good way to say this. This kind of is G of B, Jeff. I know. Okay. if I do this, this ends up being g of b minus g of a. So if I define my stuff to start at 0, g of b would go up to here. Is that cool? If I started at 0, is that all right? If I define it to start at 0, g of b would go up to here, correct? G of a would go up to here, correct? So then g of b minus g of a would equal what this guy says. Okay, stay with me. What did we just say g of x is? Big ass f of x plus c, correct? So what's g of b? G of x is big ass f of x plus c. What's g of b? Big ass f of b plus c. Minus, what's g of a? Big ass f of a plus c. And what do the c's do? Cancel. All right, let me rewrite what just happened. You don't even currently, I know, it's a lot of notation, a lot of symbols. What does this mean? Antiderivative. What does this mean? Area. So again, you don't know this, but you will in a minute because we'll do a couple concrete examples. We just showed how to do the integral using antiderivatives. So let me write this down again. This is FTOC 2. This is the one that's going to rule our life for the rest of class, which crazily enough is just this and next week. It's insane. Holy shit. So FTOC 2 says this: the integral from a to b of a function is equal to the antiderivative evaluated at b minus the antiderivative evaluated at a. That is FTOC 2. That is the connection. And if you go back to the thing we just did earlier, where we did f of 3 minus f of 0, that's exactly the shit, yes? Wasn't it 0 to 3? And we said f of 3 minus f, ooh, it looks like it's the same. Well, now we just proved it is the freaking same. So, if I wanted to, let's do a concrete example now. Because I know you're all like, dear God, enough with the notation. So what if I want to integrate from 1 to 3? It doesn't matter, Jeff. X squared dx, yes. So one way to say this is, I want the area under the parabola between 1 and 3. Right? But another way to say this now is, I want the antiderivative evaluated between 3 and 1. What is the so now the first step on this problem, instead of doing the I shit, we are now at the point where we have the shortcut. What is the antiderivative of x squared? We did it earlier. The new power would be 3, and then I have to divide by it, right? Now, here's the notation you use. There was a lot of possibilities for how we could do this. We just chose to do it. Not we. People before us chose to do it this way. We say, this is the antiderivative, and we want to evaluate it between 1 and 3. This symbol means, evaluate this function between 1 and 3. So are you with me? So in symbols, if this is little f of x, what's this? Big F of x. So all this tells me to do is to do big S f of 3 minus big S f of 1. That's what this means. Evaluated at this point minus evaluated at this point. That's what that means. Are you with me? So you don't have to write this. I'm just putting that symbol there. So how do I do this? It would be 1/3 times 3 cubed minus 1/3 times 1 cubed. I see what you're doing. Yeah, 27 thirds minus 1/3, 26 thirds. Yeah, I'm with you. Okay. 8.66. Maybe. So we just proved that the thing we did on that sheet, man, where's my work? Who knows? The thing we did here, where the bottom seemed to be, that's exactly what we can do. We can do the antiderivative of this, and then plug 3 in and plug 0 in and take the difference, and we'd be done. We don't have to do all this shit. Now, just to be really clear, in 5.2, you got to do all this shit, because that's the point of 5.2, right? 5.3, the point of 5.3 is, dear God, give us a shortcut. Alright, so let me give you this. I know we don't have the most time in the world, but I want to do a few of these with you. Oh yeah. Look at the side that's got a bunch of integrals. Don't look at the side with a bunch of words. I'll just confuse us. Anything. Don't look at the side with a bunch of words. I heard somebody go, whoa. I mean, you can if you want to, I can't stop it. Yeah. It cancels out. Both big ass F's have a plus C, and you're subtracting. Hold on. I mean, I see what you're saying.
It's not like.
I got you. Hold on. Yeah, that, Lindsay, it's a little unsatisfactory, but we don't write the C here simply because we know it's going to cancel out. So you could argue that technically that's wrong then, but it's just the wrong that we all agree that we're cool with. Yes? I'm doing.
I didn't get a worksheet.
Don't take it personal, Kevin. I'm sorry. That's just me showing up. Oh wait, you're not. There's no company. Alright. I'm so quick to assume it's my ability to count. Okay. So, first thing I want to do, let's just look at the bottom first, actually. Let's try this first one right there. Number 2A. This good old FTOC. What's the difference up here? What's going on with these guys?
There's no number C.
There's no limits. There's nothing. There's no from to. So I'm going to talk about that in a moment. Can we all try 2A? Go ahead and try to do 2A. Alright, this was not too bad, right? You can look at this two different ways. You can either, the 2 goes to 3, divide by 3 so the 3's cancel, or more better. That's exactly what I was about to say. More better. The 3 just goes back up. Either way you do it, you get freaking x cubed plus what? X. Evaluated between -1 and 3. Yes?
You don't do the plus C.
Beautiful. We just had a discussion about it over here. For definite integrals, these are definite integrals. The first set are called indefinite, and now that name totally makes sense. These are defined between something and something. The first ones are not. So these are definite integrals. I never put plus C because they would cancel. So if I did put plus C, let's just do it. Plus C. Okay. Plug a 3 in, I would get. Plug a 3 in, I get 27 plus 3 plus C, yes? Minus, plug a -1 in. -1 minus 1 plus C, yes? You guys with me? Notice what I did. The most common mistake is people forget to put these parentheses. What am I subtracting on the next step? F of A, the entire F of A. Not just the first piece of it. So you got to put the whole damn thing in parentheses. What will the C's always do? They will always cancel, yes? C minus C. So that's why we've just chosen, don't write that shit. If you want to, go ahead. I don't care. They'll cancel out. And maybe that way you just, put a plus C all the time. You won't forget it. So then you end up with what? 30 plus 2, 32. Is that all right? You guys alright? Okay. See some quizzical looks, but nobody's saying anything, so. What about B? What's the antiderivative? Tangent, yeah, so this is what I mean. The better you know your derivatives, the easier this stuff's gonna be, and I wanna go between 0 and pi over 4. I haven't done much. Right, so the antiderivative of secant squared is tangent, theta. And then I want to evaluate between those two. And on a test or a quiz, I'm going to say, I want the exact answer. So you got to know how to do tangent of pi over 4, for example. What's tangent of pi over 4? 1. What's tangent of 0? Zero. Good. That's weird. Look at that. Funky ass secant squared, and I go from funky ass 0 to funky ass pi over 4, and the answer's 1. That was not expected, yes? By the way, real quick, do you guys remember how to check your work? Check your work. Taking a derivative won't work, because what's the derivative of 1? 0. Okay, so what I mean by check your work is check to make sure this number's correct, right? So if you put secant squared in here, and how do I put secant squared in here? I can do 1 divided by cosine theta, or x in this case, squared, 11. Zoom 6. Oh shit, I'm not in radians. This is not my calculator. My calculator died. There we go. That looks like what secant's supposed to. And this is squared, right? So that makes sense, it's always above. Let it finish doing that. Where do I go to try to do this integral in the calculator? Second trace, and then the thing that has the integral sign. Now that's totally looking like something we know. And the cool thing is here you can put in from, what was it again? It was 0, from 0 to pi divided by 4. Kick ass! I mean, look at that shit, guys. Gaze upon that shit. What are you saying?
What is that saying?
Huh?
What is that telling me the area?
Tells you the derivative. Yeah. Okay. I'm not sure what this is actually down below. It's too bad for me. But there, I'm sorry, not the derivative. The integral is 1. That's what's important. So you can check every single definite iteration question I ask you. You can check it on a test, on a quiz, on a homework, whatever, right? You don't have to go to check answers or whatever. You can just check it yourself. Go to Reddit, cheat at math homework, whatever you want to do. Don't do it. So, I go there sometimes and mess with you. All right, do you guys start to see now? Notice something about part C. I want you to notice. Remind me what that big ass S means. Something. Do you guys see how any constant I can just take it out? That's like GCF shit. I'm summing a bunch of things that all have a 2 in it. So I can do this. Do you see how they help me a little bit? What's the integral of 1 over x? Tell me again. ln x? Well, yeah. If I do this, what am I going to get? Because I've done something wrong. So if I try to plug a -1 in, what am I going to get? You shouldn't have to put it in your calculator, but if you put it in your calculator, calculator's going to go, what the hell is that? Can a natural log handle a negative input? No. Is this function cool with these inputs, 2 over x? What's the only number this function is not cool with? 0. So this integral must exist because this function exists between those 2 points. So of course there's an area for it. So something went wrong. I forgot my absolute value. See that? Saves your ass. Natural log is not allowed to exist on the negative side. That's why the connection between 1 over x and natural log is the absolute value. Therefore, the domain is the same. Now this thing can handle it. So when I plug in -1, it's the absolute value -1. Absolute value -e. Dang it, forgot my little negative down there. What's the natural log of 1? 0. And what's the natural log of e? 1. So I get negative 2. Very quickly, by the way, what does this symbol mean most basically? Not antiderivative. What's this symbol mean? Sum. Good, but what's it get me? Area. What answer do we get? Area can be negative. Thank you. Thus concludes my TED Talk. Not a damn thing wrong with area being negative when area is some physical property or something. You can have a negative area of a shed, but you can't have a negative area when the area represents profit or velocity or whatever. You can have a negative of those things. Okay. So last thing about for today is maybe sort of last. Yeah, last thing for today. When I don't have limits, the integral, this is just equal to the big ass F. So this question, when I don't have limits, this only wants the antiderivative from it. When I have limits, I don't just find the antiderivative, I evaluate it between the limits. So when I don't have any values, I just have to find big ass F. I just have to find the antiderivative. So what would the answer to this first one be? What's the power become? Negative 1, because you go up 1, because you're doing the opposite of derivative. Almost done with that piece. Over negative 1, so it just becomes negative, yeah? Minus 3x. Plus c, yeah, that's where you're going to lose points if you don't put the plus c. Like so many points, no. Normally, if you miss like for every 2 or 3, I take a point off. You know what I mean? I don't want it to kill you, but I got to make the point. It's not true without the plus c. Alright, so tomorrow we'll finish this up. We'll have that quiz first thing. And I'll tell you what I decided about this quiz. Okay. Thank you guys for putting up with me. This is some cool shit.